Bismillahirrahmanirrahim. Alright class, Assalamu alaikum. Welcome to the first lecture of week 5 where we'll study the physics component of electromagnetic fields, this course. And actually we had spent great deal of time in studying the mathematics, which is the language of any physical science, or especially the language of electromagnetics. So we have spent a great deal of time in that, but we should always remember that this course, or the subject of electromagnetism, has got its root deeply rooted in physics, and all the results that have been derived, that we would be deriving, were based on fundamental physical experimentation that were performed, years ago. So before starting the first chunk of electromagnetism, that is electrostatics, remember that chart which I gave you at the end of the last week, very end. So electrostatics is the first major chunk, and that chunk is really necessary to understand magnetostatics. Why? Because we'll spend a great deal of time in studying electrostatics because it is comparatively easy. Then when we'll move on to magnetostatics, we'll keep referring back to that we did so and so in electrostatics, so and so is also true in magnetostatics. So it is really necessary to pay attention while studying electrostatics. Okay, so before discussing this, I want to give you a scenario. Let's say I take a random student and I call him student number 1, and another student and I call him student number 2. Both are students which who are working in my team, let's say. Okay, that this is the scenario, keep that in my mind. And we are living in some some planet, maybe Mars. So let's say this is Earth, all right, and we know nothing about this planet. So we are sending our first experimental mission to explore this universe. And let's say I've asked one of my students to go to this planet, which we call Earth. Student number 1 goes here, and student number 2 goes to the moon. All right, and that is also a heavenly body, if not a planet in universe. Okay, so what we are doing, we are performing some gravitational experiments on these two planets, and I asked one of my students, student number 1, to land here, and asked student number 2 to land here. And what is their task? Their task is to map the force field surrounding these heavenly bodies. As a consequence of week 1 lectures, you should now understand that whenever there is a mass, there is a field surrounding it. Okay, so whenever there is a source, there is a field, and whenever there is a field you can sense, there must be some source of that field. So we said that in week 1 lectures that the source of gravitational field is nothing but mass. So there must be some bounded region surrounding this planet Earth, okay, over which the effect of that field can be sensed. Okay, and that field, which is the gravitational field, can communicate with another gravitational field which is present in the vicinity, in the surroundings of a mass. Okay, so definitely this gravitational field is not going to talk with the electrostatic field. This, at least we want to develop our concepts as such. Okay, so similarly there will be some field, some bounded physical three-dimensional space, bounded space, just like this, surrounding the moon, but with different dimensions. Obviously the radius of this bounded region will be much higher as compared to this one, because mass is higher, so its gravitational field should be larger. This is what we expect, and this is what it is. So we know that the mass of Earth is how much? If I am correct, it is approximately equals to, with a dot, approximately equals to 6 exponent 24 kilograms, and mass of the moon is approximately 7 point, if I am correct, it's approximately this. So never mind, the mass of the Earth is approximately 100 times larger as compared to the mass of the moon. So now student number 1 lands here, student number 2 lands here, and their task is to evaluate the force field using Newton's law, m1 m2 upon r square. We all know this law. Okay, so this is Newton's law, not Newton's law, because we are Newton is a scientist on the Mars, so he is not Newton. Anyway, तो ये न्यूटन का जो लॉ है, यूनिवर्सल लॉ ऑफ ग्रेविटी, this is the formula that I have given both the students and asked to apply that formula. And if student number 1 is on this planet, he should use ME, and when ME to find the force field of Earth, and the student number 2 should find the force field of the moon, and he should apply replace, instead of m1 he should apply m1 should be equals to mm, which is the mass of the moon here. Okay, so where r is the distance between the second mass which he has in his rocket with him, and student 2 has also got a mass which he has got in his space shuttle. All right, so after landing here, they have been assigned their tasks to map the field, evaluate the force within the Earth field, and within the student 2 has to evaluate that formula within the field of the moon, and at various locations. All right, various location, different height with respect to surface, and different locations as well, north, south, east, west, so on and so forth. But somehow I forget to tell them how much amount of mass they should use to test the field of their respective heavenly bodies. So let's say student 1 used the 1 gram a mass of 1 gram to evaluate this formula, rather student 2 rather used 10 kilograms, because I did not tell them which mass to use as m2, or the test mass on which the force is being applied by their respective planets or heavenly bodies. Moon is definitely not a planet, so heavenly bodies is the right term to use. All right, so you can expect that if student 1 would use the formula to find Fe, force of the Earth on the body, what he would end up in would be G times this multiplied by this, and this is nothing but 10 raised to minus 3 kilograms. So multiplying Me and this test mass, which is m2, would give him 6 exponent 21 divided by r square, or write it more neatly, 6 exponent 21 times G divided by r square is what he'll get. And since G is constant, replacing different values of distance between this and the center of the Earth, that is r, he will be able to map some force field surrounding this earth. मास 1 मीटर दूर है तो इतनी फोर्स है, और 2 मीटर दूर है तो इतनी फोर्स है, और 6 मीटर दूर है तो इतनी फोर्स है, और 6 किलोमीटर दूर है तो इतनी फोर्स है. These are the field mapping. Okay. And student number 2, which landed on moon, would try to use the formula, this formula, and this formula is the same, but this time he is using mass of the moon, which is this, times 10 kilograms m2. This time test mass m2 is 2 kilograms, so, sorry, 10 kilograms, so multiplying the 2 would end up in 734 exponent 21. I want to keep the power the same, that's why I made it 734 g times r square. Okay, so when both of them, student 1 and 2, would finish their experiment, and they will be called back to their headquarters in Mars, somewhere in Mars, and they would show me the results. Student number 1 will show me the results, and student number 2 will show me the results. Their data would suggest something which is contrary to our experience and science, that the data of student number 2 will give us approximately 100 times larger force field as compared to the one which will be given by the student number 1. How we can find it? We can find it by dividing Fm and Fe. This entity would end up in something larger than 100. You can do it. You can do it. You'll end up in something. So it means that the data would give us, that would suggest that the force field of the moon, or in other words, the gravity, the intensity of the gravity or the gravitational pull surrounding the moon is 100 times larger as compared to Earth, which is definitely wrong. So what's the fundamental flaw in this whole scenario, in this whole experiment? The fundamental flaw is that we want to evaluate the field of Earth, we wanted to evaluate the field of moon, gravitational field, we wanted to plot the force field or the gravitational pull surrounding the Earth, we wanted to plot the or map the gravitational pull or force field surrounding the moon. Yes, so that pull should be defined such that that pull should not depend on the test mass. Okay, the fundamental flaw is that we have used different judges to evaluate different fields. We should have used same judge to evaluate different fields. Gravitational fields of different planets should be judged by the same judge. Only then we are doing a fair comparison. Otherwise, that experiment is fundamentally flawed. Okay, so if we are talking about the gravitational field of Earth, then in that field there should be no reference to the test mass. If we are interested in the gravitational field of moon, so in the definition of that gravitational field of the moon, there should be no influence of the test mass, because we are not interested in what the test mass is. We are interested in the gravity of the source of that gravity. Okay, we are interested in the effect of the source of that gravity. Effect is gravity and source of that gravity is that Earth. So in the formula for gravitational field or the force field, there should be only consideration of Earth and nothing else, no other body. Okay, so it means that we have to assign the same judge here. It means that the fundamental flaw was of the person who sent their student, his student over there and did not explain what to do, or if the student were not able to decipher that they should use the same judge here. And since we are working in SI system, I should be explicit about the judge, that the judge should be the 1 kilogram charge. Student 1, you should also take 1 kilogram charge. Student 2, you should also take 1 kilogram charge, otherwise your experiment will give flawed results. Now, if student 1 had used this and student 2 had used this 1 kilogram as a test mass, then the situation would have been totally different and that would have been totally correct. उस केस में हमें फोर्स अर्थ की ज़्यादा मिलती. So it's about common sense. We normally say that someone is number 1 batsman in the world. We say that Tendulkar is, for example, number 1 batsman in the world, but he never played well against Shoaib Akhtar. Everybody knows it. So the best, if we are giving us the qualities of some person as if we are defining some person that he is a calm person or he plays good cricket, so that cricket or that property of being calm should be universal to him. It's not like when everything is good, जब सब कुछ अच्छा होता है, he stays calm, but whenever something irritates him, he becomes angry. So that person is not cannot be classified as a calm person. So the situation surrounding that person should never define that person's qualities. All right. So I think I'm trying to make myself clear, but never mind. So if I want to define the field of this heavenly body, so that definition should have only tazkira of this heavenly body. There should not be any tazkira of this, any involvement of this surrounding. All right. So if Tendulkar is a good batsman, he should have played well against Shoaib Akhtar as well. All right. So that's on the lighter note. No doubt he is a legendary batsman. Never mind. So, but keep this scenario in mind. I have spent quite a lot of time on this, but keep this scenario in mind, and you will be able to relate why I have explained so much on this. Okay. So now let's start off with this. Coulomb's law and electric field intensity. So this is the very first law which we'll be discussing, because it defines very fundamental nature of the charge. What experiment Coulomb performed, he was a tremendous physicist. What experiment he performed, we are not going in that detail. What instrument he used, we are not going in detail. We are just going to take the crux of it. He had a torsion balance. Torsion balance is an instrument which has got a needle pivoted at some point, all right, and we have got a scale which can measure force in Newton, 0 Newton up till 0 Newton up till I don't know, whatever the maximum scale can be. Okay, force max. Okay, so what he did, now this needle can move like this about this pivotal point. So here he charged this end by a known charge Q1, and he took another a very thin probe, and he charged the end of that probe by a known charge, and then he brought this probe closer to this Q1, so this needle deflected. So the distance, let's say, between these two is capital R. So after performing several experiments, meaning after taking several different charges here, like charges, dislike charges, distance, he varied distance and made a lot of experimentation, and he concluded that two charges, they feel the presence of each other in terms of force. All right, so there should be some field. They were not physically touching each other, but there was some imaginary field surrounding this, which can be felt by the other charge, in terms of some force. And he concluded that the force, the magnitude of the force, was directly proportional to the product of the magnitude of the two charges, and was inversely proportional to the square of the distance between them. Okay, and this was his first observation. All right, so as we know that force is a vector quantity, so only defining the magnitude is not sufficient. We should have also direction of that force, which is given by the unit vector of that force. So he also gave us a very useful insight into the direction of the force, that I'm not going to write it here, but we all know that like charges attract each other and dislike charges repel each other. Sorry, dislike charges attract each other and like charges repel each other. So this is what he observed through his experiments. And later on, not later on, in the same experiment, he also said that the force acts along the line joining the 2 point charges. So if I just remove the whole experimental setup and focus on the charge Q1 and the charge Q2, okay, so these were the two charges, and the distance between the two charges Q1 and Q2 is given by this variable r. Okay, so now this point charge Q1 is applying a force on this Q, and let's say both are the positive charges. So both are repelling each other. Repelling meaning दोनों एक दूसरे से दूर जाएंगे. Both will push each other away. So pushing each other away can be in this direction, it can be in this direction, it can be in this direction, it can be in that direction. So he also solved that problem by saying that the force on each other, the force on one charge due to the other, acts along the line joining the 2 point charges. So the force on this charge Q2 due to Q1 will be along the line joining the 2 charges, and since both are positive, so the force is not only along this line but also it is repulsive. So we'll call this force on 2 due to 1, force on 2 due to 1, and this should be a vector quantity. Similarly, since force, Newton's third law, right, equal force applied oh my god, I forgot the exact statement. So force on Q1 due to Q2 is given by this. Okay, it's repulsive again and acting along this line joining the 2 point charges. Okay, so had the point charges been opposite in nature, one negative, the other is positive, had they been like this, so in that case the force on 1 due to 2 will act along this line and that will be attractive. So force on 1 due to 2 will be from left to right, Similarly, force on 2 due to 1 will be attractive, acting along the line joining these 2 point charges, and attracting, so coming towards each other. So how can we give the direction to the force? Magnitude, we have talked about magnitude. How we can give direction? Let's say I am interested in force on 2 due to 1. So force on 2 due to 1 is in this direction. So if I know the point at which q1 is located, and if I know the point at which q2 is located, so it means that I can find a vector which starts from 1 to 2, which starts from 1 and goes towards 2. So I can find a vector r12. So since as soon as I can find this vector r12, I can easily find a unit vector. How? You all know now. Divide this r12 by its magnitude. So the direction of this is nothing but magnitude of this multiplied by r12. Similarly, the force on charge 1 due to 2 should be equals to the magnitude, and magnitude will come out from this, and we'll talk about that later. But this time the direction of force is totally opposite as compared to this one. Alright, so now we have to find a vector that starts from this point and terminates at this point. So a vector that starts from 2 and terminates at 1. Okay. So previously we had the one which starts from 1 and terminates at 2. So head is here. So if head is here, so we should use 2 and 1, and if head is here, then we should use 1 and 2 as per our previous practice. So I should write 2 and 1 here. Okay. So F12, force on Q1 due to 2, is equals to magnitude of force due to 1 on 1 due to Q2, which will be given by this formula, and the direction is nothing but the direction of the unit vector which is associated with this r12. Okay. Alright, so the magnitude, let's talk about the magnitude. If I remove this sign, I'll have to introduce a constant of proportionality, and in SI system the constant of proportionality is nothing but 1 upon 4 pi epsilon naught, where the units will be, if I just cross multiply, we'll get on the left hand side Newton meter square divided by Coulombs square is the units of K, where epsilon naught is nothing but permittivity of free space, and this permittivity is nothing but the ability of a material to allow establishment of field, and to be precise, electric field. Okay, so let me repeat, the ability of a material to allow establishment of electric field within itself is permittivity. Okay, so we are epsilon naught means that we are interested in the ability of free space to allow establishment of electric field within free space, so that would be epsilon naught. Okay, so for free space we have got standard value 8.854, exponent 10 raised to minus 12. Okay, 10 raised to minus 12, which is approximately equals to 1/36 pi zarab 10 raised to minus 9, and the units are farads per meter. Okay, so permittivity is nothing but, if it's a normal English word, it has nothing special about it, except that we don't use it in English so much we use it in physics. So permittivity, if I just translate this from English to Urdu, it will be सरायत करने की सलाहियत, just like we have soul, इंसान के जिस्म में रूह सरायत की हुई है, soul has been some people are brave, they're called nidar लोग होते हैं. If you watch a horror movie, some people will get scared pretty easily, and some won't show any sign of any fear. So for nidar people, we will say that इसके अंदर खौफ कम सरायत किया हुआ, he has smaller permittivity towards fear. And the people who are थोड़े से डरपोक जो होते हैं, so हम उनके बारे में कहेंगे कि इसके अंदर खौफ सरायत कर गया, permeate कर गया. Okay, so there are two terms, permittivity and permeability. Both have got the same meaning. सरायत करना, अंदर ऐसे दाखिल हो जाना कि throughout that it gets established throughout the body. Okay, so सरायत करना, permittivity और permeate करना एक ही मतलब है, have got the same meaning, but the ability of a body to allow establishment of electric field is permittivity, and the ability of a body to allow establishment of magnetic field is permeability, जिसको हम mu से represent करते हैं. So anyway, so permittivity is nothing but the property of a material. Okay, so now we can say that magnitude of the force which is given by Coulomb's law is nothing but Q1 Q2 upon 4 pi epsilon naught and r square, where r is the distance between the two charges. And in this case precisely, if I would like to write the formula for force on charge Q1 due to charge Q2, I would write the magnitude first, which is according to this expression, Q1 Q2 upon 4 pi epsilon naught, and R1 and R, which is the distance between the two. Okay, so when I was evaluating this force, the force on Q1 due to Q2, I had used this distance. Okay, because force is from right to left, so I needed a vector which would have the head on Q1 and tail on Q2. Okay, only then I will get this direction, a vector in this direction, and a unit vector in this direction. So a vector in this direction is R12. So a unit vector in the direction of R12 will give me the direction of the force as well. Okay, so for force 12, we'll use the vector R12, its magnitude actually in the denominator according to this formula, R12 squared, and the direction is given by this. So right now, up till now, I have written the magnitude only, and the direction is given by this unit vector, which is AR12. Okay, and for force on this charge Q2 due to Q1, I would write magnitude, which according to this formula is given by Q1 Q2 divided by 4 pi epsilon naught, 4 pi epsilon naught. Up till now there is no difference between these two, okay, divided by what? Divided by the distance square. So since I am using this this force, I am evaluating this force, that is force on Q due to Q1, Q2 due to Q1, force on Q2 due to Q1. What I would need? I would need, and we know that both the forces are repulsive, so they are, you know, they are pushing each other. So it means that I would need a vector which would have a head here and its tail here. So I would need R21, okay, head on 2, tail on 1, as per our previous practice, okay. So we would need this vector, and the unit vector in the direction of this vector would be AR21, okay. So what I need in the denominator, I need the distance squared. So for distance I need to have magnitude R21 magnitude squared multiplied by the unit vector AR21. So by the way, whether you take the magnitude of R12 or R21, that would be the same, no issues at all. So actually you can see that the magnitude of F12 and magnitude of F21 both are the same. The only difference is in you know, the unit vectors. This vector is the one which points from 1 to 2, is it? From 2 to 1, because head is on 1, tail is on 2, and this vector is the one which starts, which points in the direction of 2 from 1, okay, 2 from 1, head on 2 and tail on 1. So I can simply write that F12 is nothing but minus of F21, and this minus will affect the direction only, okay. So all right, so before closing this session, I would like to discuss one little point further, and then we'll move on, okay. So one important point about Coulomb's law is that Coulomb's law is linear, and the consequence of being linear means that superposition theorem can be applied, and you have applied superposition theorem in the case of circuit analysis. And what was that? Let's take a very simple example to emphasize on this. Let's say we have a source of 1 volts and a resistance of 1 ohms, and we want to calculate the effect of this source, which is current. So you can, using Ohm's law, you will say that the effect of this source on this resistance is that a 1 ohm current will be flow through this. So if I would ask you that, okay, if I multiply the input by 2, how much would be the current? If you already know that if we had 1 volt, the current was 1 ampere, you would say just multiply the input by the same value, the same real number which you multiplied, which you use to multiply the input. So if input is multiplied by a real number, the output would be multiplied by the same real number. This is the consequence of linearity, and this was possible. Doing this was possible because the circuit was linear. So this is actually superposition theorem, okay. So I can say that if input is multiplied by n, then output will be multiplied by the same number, real number n, okay. Similarly, the second consequence of linearity was that, let's say if we had 2 sources, 1 volts and 2 volts, and this is the same 1 ohm resistor, and we want to find out the effect of these 2 sources on this resistor, then that effect is let's say current. You can simply say that okay, these 2 sources combined together will flow a current of, the output will be 3 amperes. Okay, these 2 sources will push a current of 3 amperes, or the output will be 3 amperes. since this is a linear circuit and you can apply superposition on it, so what you can do, you can take the effect of individual sources, you can measure the effects of individual sources. Okay, the effect of this source is that the current will be which will flow through the circuit will be 1 amperes. Okay, you remove this source and see the effect of this source only, that will be 1 amperes, and now you remove this source and see the effect of this source only, you will see that the effect of this source through this circuit will be 2 amperes. So if you add the individual effects, you will get the effect of the two individual sources combined together. They will affect the circuit in this manner that the total current or the output will be the 3 ampere current flowing through this resistor. Right, so this is again the consequence of linearity. Had the circuit been not linear, you could not have applied this superposition, that the effect of the individual source, if add up together, will give you the final effect of all the sources combined together. So this is, you all know, superposition theorem. All right, so with this I would like to end today's lecture number 1, and inshallah we'll meet in the second lecture. Okay, assalamu alaikum.